All right. Next one I'm going to do is number 48. And 48 is a little more interesting. In this one, Sam, whose mass is 75 kilograms. So he has a mass equal to 75 kilograms. Straps on skis and starts down a 50-meter high, 20-degree frictionless slope. So it's 50 meters high, so it's 50 meters on this side. But the slope is like a triangle going this way, where the angle here is 20 degrees. He's on his skis right here going downhill. Okay. A strong headwind exerts a horizontal force. So there's a force this way coming from the wind, which is equal to 200 newtons on him as he skis. Use work and energy to find his speed at the bottom. So we want to figure out what his velocity is down here at the bottom of the hill. All right. Now the interesting thing is this would be a very trivial problem if they didn't put the wind in here. But because they put the wind in here, now we have to do work because it's an external force. It's not just gravitational potential being converted into kinetic. But we're still going to do it the same way, but we have to do energy initial plus the work external is equal to energy final. Okay? The energy initial is gravitational potential, so that's just mgh. That's the height he is. Okay? Now the work external is going to be this force. But remember what work is. Work is equal to FD cosine of the angle. Right? So the force in this case is going to be, or I'm just going to write this out, FD cosine of the angle. And then the energy final down here is going to be all kinetic energy. Because there's no gravitational potential. Gravitational potential is 0 at the bottom. Okay? All right. And we want to solve for V here. Okay? But what we got to do is figure this out. The D, the distance, is going to be this distance that he's skiing here, D right here. So we got to figure out what that D is, because we're not given D. We're just given D in 50 and 20. But we look at this and we say, oh, well, the sine, that's just a triangle, and the sine of 20 degrees is opposite over hypotenuse, or 50 over D, or D is just equal to 50 over the sine of 20. So we know what D is. Okay? We know what the force is. And the force is going this direction. Now what we've got to do is figure out this angle, and then we have to look, well, the force is going this way, but which way is the velocity, or which way he's going? He's actually going this way. So that this angle right here is 20 degrees. But the angle, this is the displacement vector here, for theta has to be the angle between the force and the displacement vector. Or in this case, the angle is going to be equal to 160 degrees. Remember, you don't put in positive or negative here. You just put this in the angle, and the angle being greater than 90 is going to make that become a negative. So now I can plug all that in. First of all, I'm going to solve it for V squared, because that's what I want. So I'm going to multiply by 2. So I get 2 mgh plus 2 fd cosine theta is equal to mv squared. Divide by m. And then we're going to get V squared is equal to 2GH plus 2FD cosine theta over M. Now be careful, when I divided by M, this whole side was divided by M. But those M's cancel out, but the M still is under this term over here, which is why I solved it like that. And then V is equal to the square root of 2GH plus 2FD cosine theta over M. Alright, so now I just plug all that in. So I got V is equal to the square root 2 times 9.8 times 50 plus 2 times 200 times D, but D is equal to 50 over the sine of 20 times the cosine of 160. All divided by his mass, which is 75. And then if I plug that in, I get that V is equal to 15.7 meters per second, or 2 sig figs, 16 meters per second. All right, the biggest difference here is we had to deal with the work external. Remember, you still put it in as a positive d cosine theta. You just got to make sure you get the angle right, the angle between the force and the displacement vector. And then we had to figure out d. D is the whole distance he's traveling. And since he's traveling down the slope, we had to figure out what d was. So that's how you do number 48. Okay. The next one we're going to do is number 51. All right, and in 51, it looks like this. 51, we have this. We have a pickup truck. Here. And we have a ramp into the pickup truck. Here's the ramp. It comes down like this. And this is 1 meter high. Okay. And then we have a package over here. And there's a spring that connects it to the wall. And the package gets shot up into the back of the pickup truck by using the spring. Okay. The spring constant, K, over here, is equal to 500 newtons per meter. The spring is compressed 30 centimeters. And the mass of the package is 2 kilograms. So part A, we want to find out what is the speed when the package gets to the back of the truck. Alright, so again we do this as energy initial is equal to energy final. It's starting down here with no velocity, and this is going to be our gravitational potential equal to 0 at the lowest point here. So the only thing it has to begin with is spring energy. And when it gets into the pickup, it went uphill, so it gains gravitational potential energy. So this becomes mgh plus 1/2 mv squared, because it's going to have a velocity when it comes in the back. That's what we want to solve for. So that's what we're going to do. We're going to solve this for the velocity here. So we're going to multiply by 2, because that gets rid of the 2, and we're going to move the mgh over here. So it's going to become kx squared minus 2mgh is equal to mv squared. And I'm going to divide by m, and I'm going to get that v squared is equal to kx squared minus 2mgh, all that over m. And I'm going to take the square root of that, kx squared minus 2mgh over m. So v is equal to square root of, I have k is 500. X we have to convert, this is 0.3 squared, minus 2 times 2 times 9.8 times the height is 1, all over 2. We do that, we get a velocity of 1.7 meters per second. Alright, so that's the velocity that it enters the back of the truck. However, what we need to do in part B is it gets a little tricky. In part B they say a person spills a drink. A careless worker spills his soda on the ramp. This creates a 50 centimeter long sticky spot with a coefficient of kinetic friction of 0.3. So down here where it's in the flat part, we have friction now. And the friction has a kinetic coefficient of 0.30. And that is a distance of 50 centimeters or 0.50 meters. Alright. Now, because of the sticky spot, we want to know, will the package still make it into the truck? So we're going to do this as part B. We're going to do energy initial is equal to energy final. And in this case, energy initial is still the same. It's still spring energy. Nothing's changed there. This is still going to be mgh plus thermal energy. Now we're not going to put kinetic energy in here because we want to figure out how high this makes it. If h is greater than 1 meter, it's going to make it in the truck. But we don't know if h is less than 1 meter, it's not going to make it in the truck, because we have to take into account the thermal energy. So there's no kinetic energy over here. We're just figuring out where it stops. So now what we want to do is expand this. So this becomes 1/2 kx squared is equal to mgh plus, but thermal energy, remember, is friction, is mu sub k times the normal force. But the normal force, when it's on flat ground, we have the normal force is just equal to mg. So this is mu sub k mg times the distance that it goes, which is the distance that friction occurs, which is the 0.5 meters. Okay, we're going to solve this for the height. So this becomes 1/2 kx squared. I'm going to subtract that minus mu sub k mgd is equal to mgh. I'm going to divide both sides by mg, and I'm going to get h is equal to kx squared over 2mg. Now notice the mg cancels here. This becomes minus mu sub k d. So when I divided both sides by mg, that's what I got. So the mg goes over here, and then here the mg canceled with that mg, so I'm just left with mu sub k d. So when I do that, I get that h is equal to, I have k is 5